So, welcome to our 16th lecture, and today we will be covering topological sort and tries. So, let's start with topological sort. Topological sort is a specific order of nodes in a given directed acyclic graph. So, what does directed acyclic graph mean? Like we have a graph, obviously. Acyclic means the graph does not contain any kind of cycles. Meaning, if we start from one node and start the edges, there is no way we can come back to the same node again. There is no cycles in the graph. That's why it is called acyclic. And at the same time, it's a directed graph, meaning each edge has a start and end point. So edges are not both ways. So let's take a look at this graph, and actually it's better to put it on the board here. So we have one node here, one node here, one node here. One. And their numbers are 5, 4, 2, 0, 3. No, this is 1. And this is 3. Wait. There's only one node. What is left for this guy? And index of this one is 3. And let's also add some edges between them. So we have this one, this one, this one, this one, and this one. So now let's take a look at this graph. Do you see any cycles in this graph? Like if we start from 5, there is no way we can get back to 5 because there is no incoming edge. If we start from 2, since we cannot get to 5 in any way, there is no way we can get back to 2 either. So as you see, there is no, you can apply the same principle to other nodes, and you will see that there is no cycles in this graph. And secondly, our edges, as you see, they have direction. So they have start points and end points. Like if it was like this, it means this edge was undirected, meaning connecting both nodes in any way. But if we have these arrows, it means the edges have direction. So it's a directed graph. And topological sort is an order that is defined on directed acyclic graphs. So what kind of order? Basically, we have the condition of each node coming, like appearing in this order before then the nodes that are reachable through outgoing edges. Meaning, if in an order 2 appears before 5, there is no way this is going to be a topological order. 5 has to appear before 2. 5 has to appear before 0. 1 has to appear before nothing. So now let's evaluate these 3 orders to see whether they are topologically sorted or not. So the first one is 5, 4, 2, 0, 1. 5, 4, 2, 0, 1.
3.
What's that?
3.
5, 4, 2, 0, 1, 3. Yeah, we left 3. Yes, thank you. Okay, so here we start with 5, and we didn't break any rules because 5 has to appear before 2 and 0, right? And that is the case. And now let's take a look at 4. Again, 4 is appearing before its outgoing edges, like the nodes that come after its outgoing edges. That's fine. And then we have 2. So now that 5 and 4 already appeared for 2, there is nothing that is breaking the rule. And now we have 0, and 0 is appearing after 5, so still no rule breaks. And here we have 1 appearing This is fine, but now that we come to 3, 3 actually appears after 1. Therefore, what can we say about this ordering? It's not a topological order. Because by the rule, 3 has to appear before 1. And that's not the case in this ordering. And let's check another one. 4, 5, 0,
2, 3, 1.
2, 3, 1. So 4, 5, we already did the check above, and 0, right now it appears after its, let's say, parents. That's fine. And then we have 2. So for 2, again, 5 was already added to the list. It's fine. And then we have 3. That's also fine because before 3, 2 and 5 had to appear and they have already written in the list. And finally we have 1. So this time, like 4 and 3 have to appear before 1. And also like 2 and 5, and that is the case. And as you see, we were able to tick all the nodes. Therefore, we can say that this is a topological order. And let's evaluate the last one.
4, 5, 2, 3, 1, 0.
3, 1, 0. 4, 5. And then we have 2. That's good. And then we have 3. That's good too. And then we have 1. That's fine. And finally we have 0. So this is also another topological order. And as you see, for a given graph, topological order does not have to be unique. There can be multiple topological orders. So, what do we have to do with this topological order? Why do we care about this? Now let's think of some applications. Let's say we want to do some prioritization among jobs. Or we are trying to build a curriculum for software engineering students. Some courses are prerequisites of the others, right? Like once you think of that, let's say like this could be like introduction to programming. And this could be data structures and algorithms. And this could be advanced algorithms. And this could be A to SP. So, but I guess like you guys understand the application, right? Like there are some prerequisites, some conditions that like you have to satisfy before being able to get another course. And that kind of dependencies can actually be shown with directed acyclic graphs. It's going to be directed because once you think about being prerequisite condition, like if a course is required to take another course, there is no way this course will be required to take this course. Because then like students would not be able to progress in their career. Or another example we can think of is job scheduling. Let's say we are trying to build a car. And the car has different components, right? And some components have to be completed before so that the following further components can be produced. Or like we can think of a computer production as well. Any kind of device production can be an example of this. Like basically you need to create a pipeline, you have some dependencies, and you have to decide on which one you should produce first, or like in what order you should execute production so that you can have a viable, you can have a working product in the end. So is this clear to everybody? And in some applications, these edges might have some weights, as well as these nodes. And under some circumstances, you might not be able to complete them all. Like you might have some budget, some time constraints, and so on. But for the sake of simplicity, we are just going to focus on the basic topological order, primitive topological order today. Any questions up to this point so far? Things are clear? Like why we need it and how, not how maybe, but like what is it? So now we are going to learn how actually we can get topological sort. So before we start, like we are going to see two different approaches with two different graph traversal algorithms. Can anyone guess which graph traversal algorithms these are? So, let's imagine these are the components that we have to produce to have the working product in the end. We are going to put together them all in the end, and then we will have a working car, let's say. So, which parts are the safest to start execution from? 5 and 4. And what is common between 5 and 4?
No incoming edges. No incoming edges.
There is no incoming edges, right? Very good. Okay, the follow-up question is, how can we detect them? How can we detect the nodes that do not have incoming edges in a given graph? So if you remember, we had different ways of representing graphs, right? Which ways were the most common ones? How about the first one? Okay, so now let's think. Let's start with adjacency matrix. How can we detect the nodes which do not have any incoming edges? Any suggestions? Yes, yo.
We can iterate through the matrix and find where there are zeros and take the common ones.
Find where there are zeros and take the common ones. Okay, let me actually fill it up for this graph so it's going to be easier to execute on that item. And we can only indicate once, and this is a directed graph. So let's see. We have an edge from 5 to 2. We have an edge from 5 to 0. We have an edge from 4 to 0. We have an edge from 4 to 1. 2 to 3 and 3 to 1. 2 to 3 and 3 to 1. Right, this is going to be the corresponding adjacency matrix for the given directed acyclic graph. So, now, can you please propose your algorithm again?
Now, if we look at where the zeros are, or the empty boxes,
Yes, of course.
here, if we see for this one, we can check there is a zero here, 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 and here. But basically what I'm thinking is if a column doesn't have a 1 in it,
Yes.
we can take it as an edge that doesn't have.
Yes.
So here, since there are ones here too,
Yes.
we cannot take them. But this columns doesn't have ones in them, so we can just.
Yep. So basically we can start our execution from 4 and 5. We said it is safe to start from them because they don't have any incoming edges. And given adjacency matrix, the way to detect which nodes do not have any incoming edge is basically to check the corresponding columns. I mean, because we represent it in a way that if there is an edge from node A to node B, we put 1 to row A and column B. That's why. If you represent it in the transformed version, then you might have to do it the other way. And then you are going to look for the free rows or empty rows. And here, like we see that 4 and 5 are the ones that do not have any incoming edges because they have no ones on the columns. So the next question is, are we guaranteed to have an empty column in a directed acyclic graph?
Yes.
Yes. Because otherwise, if everybody has an incoming edge, it means we have a cycle. And since it's acyclic, it means there must be at least one node which do not have an incoming edge. It means we will have at least one node as a starting point. Okay, we can start from there. But after we start from there, then what are we going to do? How do we know that it is safe to continue with 0 versus 2 at that point? Can we use an helper information for that? Like, we know that incoming edge count is important actually, right? We say, like, so far we were focusing whether it is 0 or not. How about keeping track of incoming edge count? Like, basically when we are checking whether a column is empty or not, it's actually very easy to keep track of the incoming edge count for a node, right? So we can have an array called incoming. For the sake of shortness, I'm going to write it like this. EC stands for edge count. And how can we fill this up? Just go this way and sum the values, right? And 2. So for adjacency matrix, we can actually create our incoming edge count array very easily by traversing over the columns. Is it clear to everybody? What is going to be our cost of creating this? Right? So now let's take a look at the adjacency list approach. So for the sake of simplicity, I'm just going to add the list here. For 0, we don't have any outgoing edges. For 1, it's the same. For 2, we have only one element in the list, which is 3. Let me do it this way. And for 3, we have only one outgoing edges, which is going to 1. And for 4, we have 0 and 1. And finally, for 5, we have 0 and 2. So, for adjacency list, how can we generate this guy?
We can iterate through
Each list?
each list, and for example, if too high, we can relate the index of each value.
Like, let's say we started from this, right? And once we see 3 here, what does it mean? There is an incoming edge for 3, right? I can just go to the corresponding cell and then increase it by 1. So I'm going to make this 1 because there is an incoming edge for 3. And then I process this one, the same is for 1. I process this one, the same is for 0. Now I see one more 1, I increase it by 1 and it becomes 2. One more 0, this becomes 2. And one more 2, this becomes 1. So what is going to be the cost of creating this incoming edge count list this time?
Of n times m. Of n times m.
Of
N times m.
of n times m.
M
What
is
is
the number
m?
of edges.
M is number of edges. Why is it n times m?
You're only going up to how many edges that exist and not through the whole thing, like it will be on.
Like, we visit each edge once, right? Why is it n times?
Oh, plus n. Sorry.
N plus n,
Yeah.
right? And indeed, we can even say like ON.
Yeah.
Actually, like if there is no edge, actually n plus m, you're right, like we are going over all the lists. So even if it's an empty list, we are going to check to see if it's empty. So I think you're right. We can say O n plus m. Any questions up to this point? Actually, we don't have to take a look at the next 2 slides anymore. Even next 3 slides. Okay, no, next 2 slides. So, now let's take a look how the code is going to look like. Basically, we start from, like at the beginning, we have the adjacency matrix approach. And for each node, our indegree starts from 0, or incoming edge count, whatever. And then, for each edge, it is from source to destination. Oh, it's actually, this is adjacency list, I think. You see? No. Adjacency matrix, yes. Once we see an edge, we basically go and increase the indegree for the destination, not the source, obviously. And likewise, we go over the list as we taught, and then we update the indegrees. So, any questions up to this point? Now that we know the incoming edge counts, what we can do is, we can just start from the safest nodes and then iterate through BFS. And every time we process a node, we can say, okay, now, actually we don't have these dependencies anymore, because this is already taken care of. Do you see what I mean here? Like if I add 5 to my list, is there any reason to keep the course, like the dependencies between 5 and other nodes that are depending on existence of 5 in the list? No. 5 is not a condition anymore because it's already satisfied. It's already in the list. So if you take a look here, what we are doing at the beginning is we are just putting all the nodes whose indegree is 0 into our queue. So this was just a conceptual thing, like we are not going to delete the edges. But now that we calculated these guys, after we execute this code piece, what is going to happen is, let's say this is our queue. Our queue is going to have, let's say this is front, and this is end. Our queue is going to have 5 in it. Sorry, like we start from, let's say we start from 0, so it's going to have first 4 and then 5 inserted into the queue. I think it's clear up to this point, right? So let's continue with the next step. Is our queue empty? No. Therefore, we get the current element. Which is our current element right now? And after that, we just put the element that we are currently processing into our result list. And since we actually process this node, what we are doing is, conceptually, we are removing its dependency, like outgoing dependency edges. What's that mean? If I delete this edge, what am I supposed to do in this count array, in this indegree array? I have to decrease incoming edge count of 0 by 1, right? So this is going to be decreased to 1. And I'm going to do the same thing for 1 as well. And 1's incoming edge count is going to be decreased to 1 too. So the thing is, let's remember which nodes were the safest to start execution from. 0 dependencies, right? If there is 1 dependency, still I cannot start that. That dependency has to be resolved first. That's why, if you look at here, we are decreasing the indegree for the destination of the edges that come from the currently processed node. But we do not push them into queue until all of their dependencies are completed. In other words, until their indegree reaches to 0. Is this clear with everybody? Because if there is still some dependencies left, there is no way we can execute it right now. We have to deal with them first. And after we processed all the outgoing edges of 4, we see that nothing is went down to 0, nothing is gone to 0. Therefore, what's that?
I think one did go to 0.
One did go to 0? No.
Oh yeah. No.
Therefore, we didn't insert anything into our queue. And we will continue with the execution. Is my queue empty? No. And now my current is going to be 5. And I will apply the same thing to 5 as well. So 5 is popped up and we actually added to our result. It's pushed back, therefore it is added to the end of the list. And I do the same thing to 5. So 5 has 2 outgoing edges. 1 is to 2, 1 is to 0. So let's say we always start from the smaller one for the sake of consistency. So we are going to get rid of this edge. But this get rid of edge thing is conceptual, as I said. And once we do that, what happens in my in degree array? We decrease the incoming edge count for 0 by 1. And now this is down to 0. What happens when it is down to 0? It's pushed into the queue. Therefore, I will have the 0 over here, right? And I will actually do the same thing for this edge. And once this edge is removed, the incoming edge count for 2 is going to be decreased by 1. And now I have another nib 0. And when I see a nib 0, I insert that node into the queue. Therefore, 2 comes here. Oh, actually, the front didn't go. That's my back. The front is still here. 5 is processed. Right? That's my end, and I add to the end of the queue, basically. Yes. Any other outgoing edges from 5? No. Therefore, I am done with processing 5. And is my queue empty? No. So this time, which node I'm going to be processing? And 0 is also added to the result. And now I'm checking outgoing edges of 0. Is there any? No. So I'm done with execution of 0. Is my queue empty? No. Therefore, I continue with 2. And 2 is my current node now. And 2 is also added to the result. And I check all the outgoing edges of 2. 2 has an outgoing edge to 3. I conceptually delete this edge, but what I'm actually doing is updating the incoming edge count for 3 and decreasing it by 1. And now 3 also has 0 incoming edges. It means all the dependencies are resolved. Now 3 can be processed too. So what I'm doing is I add 3 to the queue. And there are no outgoing edges of 2. I am done with processing with 2. So now we are processing 3. My current node is 3 now. 3 is added to the result. And 3 has 1 outgoing edge to 1. Now, 1's incoming edge count is also 0. So 1 is added to my queue. And since I have 1 more element in the queue, I will continue execution. 1 becomes my current. 1 is added to the result. There is no outgoing edges of 1. and my queue is finally empty, and I finish execution and return the result set. Not set, but result list, let's say, because the order matters. And how about the order we get in the end? Let's go back and see our original graph to see if this is a topological order or not. What do you guys think? It is. Do we have a guarantee that the execution will always visit all the nodes?
If they're connected, it should. Even
What if they are not connected?
it will
Do we still have
yeah,
guarantee?
yeah.
Because we first start with nodes with no dependencies, right? We insert them all into the queue. So even if we have some subgraphs that are disconnected from each other, we will visit them. And now, what's the next question?
We'll go back to space.
Yes. What is our time and space complexity? What's that?
I think it's
ON? Why?
that we're okay. I mean, we're checking each node, and we're also checking for its.
I mean, first off, like we construct this with like ON plus N, right? Can it be ON?
I mean, I'm just talking about the queue process.
This part? And again, like basically we have at least like N positive value in this array. And by the end, they should all go down to 0, right?
So it's
Or,
and last day.
yes. I mean, we are basically running BFS, right? The only additional operation we are doing on top of BFS is we are keeping track of this incoming edge count array. And here we have like M values, basically. The summation of all the values in this array is going to be M. Because each edge has one incoming and one outgoing end, right? Therefore, like they will be represented exactly once here. So the total value here is going to be M. And every edge is actually processed once, and then the corresponding, like the destination's incoming edge count is going to be decreased by 1. So like I will get M operation from here. But the execution of BFS is also happening, which is happening, you know, N plus M time, right? I hit to each node as well as I hit to each edge. So the total execution time is ON plus M. And the additional memory we are using here is, like this is ON, right? But we are also using the queue. Can we have more than n elements in the queue? No. So therefore the additional memory we are using is ON. So any questions about this approach? So now we are going to take a look at the second approach. So this time our question is, what if we go as deep as we can go? Let's say we start from 5. If we go as deep as we can, where are we going to hit to? Either 0 or 1. And actually that's going to be the case for no matter which node we start from. If we push a node into the list when it has no unvisited child, what will happen? Let's start execution from 5 and let's apply BFS. Sorry, DFS. Let's say first we go to the smaller child. 5 is going to go to 0. Is there any place 0 can go? No. Therefore, 0 is going to be added, right? Because all of its children are visited. And then we backtrack to 5. We have another not visited child, 2. And then 2 has 3, 3 has 1. I hit to 1. Is there any place that I can go? No. Therefore, I add 1 to the list. And after that, I backtrack to 3. Is there any other place that I can go? Do all children get visited? Therefore, I can safely add 3 to my list too. And 3 is going to backtrack to 2. Is this the case for 2 as well? I add 2 to the list as well. And 2 is going to backtrack to 5. Is this the case for 5? Yes. And I will continue finding a node that is not visited. This is visited, this is visited, this is visited, this is visited. Who is not visited yet? 4. And what I'm going to do is I'll apply the same principle to 4. And 4 is going to look at its children. Are they all visited? Yes. Therefore, 4 is going to say, okay, it's safe to add me. Is this a topological sort order? Huh? No. But what if we look at it this way? Right? So now what we are doing is actually like we go as deep as we can and we say, okay, so this guy, this depends on everything. Let's just add it to our list. And then we keep using this logic. And in the end, we basically make the topological sort from the reverse order. So is this approach clear to everybody? We are using DFS. Depending on which one is going to feel easy for you, you can go with whatever you want. And now let's think about time and space complexity of this approach. How much of an extra memory I'm using? We check visited for the nodes, right? And what is my time complexity? It's another graph traversal algorithm. It's going to be n plus n, right? But also depending on our implementation, we will either have the call stack or we are going to have our own stack. Let's not forget about that too. It's not just visited, it's also the call stack. Okay, any questions about this approach?
Do we?
That's exactly what we have done.
Is it preferable to?
What's that?
Is it preferable to use this and when we want the reverse order, and to use the BFS when we want the sort order?
I wouldn't say so because like reversing a list is it's the easiest thing in the world, right?
Yeah, it is, but time complexity wise, it wouldn't affect a lot. It wouldn't.
You mean for reversing this?
Yeah.
I mean we already get O n plus n, so nobody cares about plus O n in the end. Yeah. So that's why I wouldn't say like BFS is preferable to DFS. Any questions about topological sort? So next time you design a curriculum for your computer science department, you know which algorithm you're going to use. All right. Programming exercises are coming. And now we are going to continue with our next topic, which is tries. Tries are very elegant data structures, guys. They are super efficient for insertion, deletion. Maybe deletion is a little tricky, but not much. And search. So imagine we are building a tree, and in this tree, each node contains a letter in it. So if you take a look at this example, I don't know, is it visible to everybody? So we start from the root, and the root doesn't have any letters in it because that's root, right? Come on, I mean, it has to be different from other nodes. And rather than root, every node inside, they have letters. So let's say our dictionary contains words which I cannot read, so I'm pretty sure you cannot read either. There, this, that, does, and did. So here like we have that, there, this, does, and did. So now let's think about it. Let's do some brain exercise. What is going to be the insertion cost for such a data structure when we have a new word? Let's say we want to insert theirs into this. I think it's going to be better to draw it on the whiteboard. I'm going to clean it all. All right, we have the root here. Can somebody help me?
T. D.
Go down. H. H. Go left until
H, and then
E.
go left, A. Go down.
let's do like DFS.
Yeah.
E,
ER.
E.
and on the left,
So the H.
H.
It's on H. On H. To H.
It's not from
Part
T,
is
it starts from H.
okay. I mean, we have already made a lot of insertion exercises here, but let's do one more altogether. Let's say we want to add days. We don't have enough length for that. Let's insert something else. Do it. Let's insert do it. Let's say it's So basically we are going to start from the root. And then we are going to look for D. There is already D. We are going to get to the D. And then we are going to look for O. There is O. And we are going to look for E. Is there, sorry, I. Is there I?
No.
No. So we are going to create I as a child. And then we are going to look for T. There is no T for I. So we are going to create one more child. And we are going to put the T. But there is one thing that we should be careful with, which is we need to annotate end of words somehow. So if there is an end of word, because like in the long run it is possible that like one word, as in the case of do for example,
Or the.
or
The.
the, right? It's a word, like it might have some new children, but still it might be an end of the word as well. So we need to indicate these as somehow. You can use end of word as a new character, or you can use end of word and mark it as a boolean. So here, for example, we have the, we have there, we have that, we have this, we have do, we have does, we have do it, let's say, and we have did. So, up to this point, did you guys build some intuition about this data structure? So now the question is, what is going to be the insertion cost? Let's say I want to insert a new word with length L. What is going to be my insertion cost? L. Right? So now let's compare it with some other data structures, efficient data structures we have seen so far. Which data structures are very efficient? Let's say we are trying to insert this to a very well-balanced binary search tree. How much cost would it take to insert a word with length L? Let's say there are already n words in the tree. How much time it's going to take to find the right spot for the new word? Log n, right? I'm going to pay the log n price first. And then, what's going to be the new price that I'm paying? N, right? Because I will basically create the key and insert it there. So, in binary search tree or like any kind of tree like efficient data structure, first you're going to find the spot which is going to take log n time, and then you will do the insertion. Whereas in the case of try, that is not the case. There is nothing like, oh, let me find the point for the, let me find the spot for it. So there is no such cost. We are doing on the way, and inserting the key actually means finding the right spot for the node, for the word. Therefore, the cost that we are paying is OL. How about deleting a word? Let's try to think how we can delete a word. Like we can recursively go in, right? Let's say we want to delete do it. Like we can start from here, we can come here. And now that I hit to the end, what should I check? If this node has any children, do I have to delete anything? The only thing that I have to delete is this little dot. Right? But if it is the case that it doesn't have any children, then it has to go. How about this guy? Is this the same? If it has no children, it has to go. Actually, it's not if it has no children. If it's not the end of word and it has no children. Because it's possible that it's the end of the word of another word. Let's say we didn't have das. In that case, like O wouldn't have any other children, right? But still, I don't want to delete it because it's an end of the word. Even if it doesn't have any children, we should also check whether it is the end of the word or not. Is deletion clear with everybody? And how about the cost of deletion? It's also OL, right? I go down and in the worst case, I'm going to come up back, delete everything. And it's going to be 2L, which is OL. How about search? Now that I want to check whether there is a word called do it. What am I going to do? I start from the root, and then I go to the corresponding character first. And then the next one. And then try to go to the next one. It's not there, therefore I will say no. But once I get to the end of the word, and I see the dot, let's say I was looking for dots. I start from D, O, E, and then I get to S, and I see that there is a dot here. It means there is a word dots, right? So what is the cost of looking up? Searching. It's also OL. Everything is OL.
Would we be saving the children as a set?
It depends on your implementation. Instead of a set, you can keep an array.
And how would we know where to look?
You can keep an array, like you have to keep basically pointers to your children. We are going to look at the implementation details in a minute. As we discussed, when L is the average length of the word, all insertion, deletion, and search cost for try is going to be OL. And it actually beats the most efficient, like very efficient data structures that we have seen so far for this specific purpose. So now let's see how the implementation is going to look like. So, as I said, you can indicate end of words in two ways. You can either have a Boolean field in each node to indicate whether that's end of the word or not. Alternatively, you can think of end of word as a character. Like let's say you indicate end of word with this character or like whatever you want. Maybe this more looks like an X, or let's say that would do it. Like in that case, what would happen is like we would have these stars here. And once we get to end of the word, we will look for whether there is a children with star or not. Alternatively, you can have the Boolean field as well. So is try not clear with everybody? Okay. Now let's take a look how the insertion is going to look like. So we start from the root node as well as from the first character of the word. And then we look for the index of that letter. Like basically, you can have different representation of your children, but it makes sense to represent them in an array. This way, let's say if we are working with English, like we are going to have an array like this. This is 0, this is 1. Let's say this is 25. And this actually corresponds to A, like this is B, and this is Z. Does that make sense? We will have this array to keep track of children. And once we start processing the word, first we are going to get the first letter. And then see if there is such child already exists for the given node or not. Let's say we want to add do it again. So we are going to check whether this guy has child D or not. We start from the root, right? Does it have child D? Yes. Therefore, the creation is not going to happen. And then we are just going to make our current next. So current was this. So now we just move to here. Current is here. And my word is do it. And then I am done with process. I am right now at D. And now I increase I, and my new index becomes O minus A. I don't know what it is. I don't know which word O is in the alphabet. But let's say O is here for this guy. And this guy basically for D, let's say right now we are representing it for D. Like D has two children, right? Let's say this is I. Like this is gonna point to a node. This is gonna point to a node too. For D, for this D. Like we can have multiple D's, right? I mean, I think we already have an example. Like we have two E's, for example. Is this part clear?
So this array plus a Boolean value is a node, right? This array plus a Boolean value. I missed it. Yeah.
So since there is already O, again, I do not make any creation. So the current progress is here. And my next character is I. Therefore, my index is going to be I minus A. And right now, I see that it doesn't exist. So what I do is this time, I execute this code piece and create a new node. And then I have I here. And finally, I move forward. Right now it's time to execute on T. So my index is T minus A. And I see that there is no such child exists here. So I create a new node. And then I put the T inside. And at this point, once the execution finishes, my current node is still this guy, right? And what I'm doing at this point is I put the dot over here. Because after finishing execution of this for loop, my word is already inserted to the try. So now it's time to execute the end of the word. And once I do that, I am done with insertion of the word. Any questions about insertion? It's very simple and clear, right? All right. So now let's take a look at search. Let's say we are searching for do it right now. We start from the root. And then like we go to the next node if it exists. D is here. And then we go to the next node. O is here. We go to the next node. O. I is here. We go to the next node. Next node. T. And then we are done with execution. We are done with progressing of our word. Right? But just because this node exists, does that guarantee that I have the word? No.